This video is sponsored by Surfshark. In the 1950s, this was the most glamorous aircraft in the world, the de Havilland Comet, the world's first jet airliner, designed to fly at 40,000 feet above the weather while passengers in smart suits and evening dresses sipped champagne and picked at canapes on bone china. Undoubtedly, she is a thing of beauty. This is what they turned her into. X-Ray Victor 249 sat here at RAF Cosford in Shropshire. Most of the people who walk past her don't know what she is. That's not unusual. Most of the people who paid for her didn't know either. She started life in 1971 as a Nimrod MR-1, hunting Soviet submarines in the North Atlantic. She ended up as a Nimrod R-1, one of the most classified aircraft the Royal Air Force has ever operated. Between those two things, she did 40 years of work the country which paid for it was never quite told about. This is a story of how Britain took a commercially obsolete airliner and turned it into one of the most effective Cold War aircraft in the world, on time, on budget, and almost completely in secret. That secrecy was the aircraft's biggest advantage for 40 years. It was also, I believe, the reason it didn't survive the 41st. When the day came that the men holding a checkbook looked at the Nimrod and asked what it was for, almost nobody could tell them. But before we get there, a quick word about how the idea for this video came about, because it's a bit of an odd one. My dad was clearing out my old bedroom a few months ago and he finds this folder. Big folder, full of magazines. Warplane magazines, mine from when I was a kid. I hadn't seen them in nearly 35 years, and I'm sat there flicking through them and there's an article on Nimrod operations. Then Surfshark got in touch about sponsoring a video. The magazine was still open on my desk and I thought, why not Nimrod? So down the rabbit hole I went. Many books, a trip to Cosford Museum, one cracked tooth, and about 100 hours of research later, a 35-year-old magazine article in a dusty folder had turned into a 3-part series on the mighty Hunter. Part 1, the one we're doing now, is how Britain ended up building it. Part 2 is what the aircraft actually did out there over the Atlantic, the secret stuff, the magic circle. Part 3 is how it all came apart. The MRA-4 fiasco, 11 nearly complete aircraft cut up behind screens at Woodford, and a country that called itself a maritime nation reduced to asking the Canadians and the French for help finding Russian submarines off her coast. You can't really tell this story in one go, or at least I couldn't anyway. The thing the Nimrod existed to do was a secret for 40 years, and the thing that killed it was partly the same secrecy. Which brings me fittingly back to Surfshark, this video's sponsor. Lately, corporations and governments seem increasingly determined to control what you can and can't see online, and here in the UK the busybodies are busy trying to stick their noses into every aspect of your lives. The concept of a free and open internet feels more under siege than any point that I can remember. Surfshark is a VPN, a virtual private network, and as a network engineer who taught network security for years, this one genuinely scratches the right itch. The one where I get to guard my privacy from the eye of Big Brother. But VPNs do more than that. Surfshark helps mitigate phishing attempts, DNS tunneling, and the data harvesting practices of basically every tech company you've ever heard of. On the entertainment side, it unlocks additional content on streaming platforms by changing your geographic region, and it gets around the censorship, which matters more than it used to. A few details that actually matter rather than the usual marketing fluff. They have 4,500 servers across 140 locations, a third-party verified report confirming they keep no logs, and a warrant canary, a public notice that quietly disappears if they're ever served with a secret government request. That's good policy for any VPN and frankly should be standard. If you click the link down below, surfshark.com/aviationrepublic, use the code aviationrepublic at checkout, you can get 4 extra months for free, special pricing offer. A big thank you to Surfshark for sponsoring the channel and inspiring this particular video series. Right, onto the story. To get to X-Ray Victor 249 we have to go back. to a wet and windy Wednesday evening somewhere off the west coast of Scotland. 2,000 feet above the water, 10 men in Avro Shackleton of RAF Coastal Command are 8 hours into a 15-hour patrol. The cabin smells of avgas, hot oil, wet wool, and the 10 men with another 7 hours to run. 4 Rolls-Royce Griffon engines with contra-rotating propellers spinning within feet of the fuselage send pressure waves through the aluminium skin at a frequency the body feels more than the ear hears. The aircraft is unpressurized, the heating barely works. At 2,000 feet on a black April night over the North Atlantic, the cabin is somewhere between cold and freezing. The toilet by tradition is awful and the food is worse. The men on the radar set have been staring at the green sweep line since dusk. The navigator is trying to work a plotting table with pencils that won't remain still, nor will his tea stay in the cup. They call her the Old Grey Lady, or less affectionately 10,000 loose rivets flying in close formation. Their job tonight is to find a Soviet diesel submarine, somewhere in a piece of ocean the size of Wales. Just before midnight, the radar operator says the words that wake the aircraft up. Possible contact 2 o'clock, 18 miles. The captain calls action stations and turns onto the bearing. The co-pilot pushes the Griffons to maximum boost. What they're chasing is a steel pipe, a snorkel mast sticking a few feet out of the sea. A diesel submarine has to come up to breathe every few hours, run its engines and charge its batteries. If the crew are lucky, they might even get a photograph, the hull, the sail, anything to identify which boat it is and report a Soviet submarine where it shouldn't be. But the boat is not blind. They can hear the Shackleton's radar long before the radar can see the mast. Cat and mouse on top of looking for a needle in a haystack. The pilots begin a descent towards the sea, 300 feet above the surface on a black night on instruments. At 1 mile they fire flares to light up the night for the camera, but the contact is gone. Maybe the Soviet captain heard the radar sweep, dropped his mask and is now sitting 60 meters listening to the Shackleton burn fuel overhead. The ocean is too big and there are far too few Shackletons. They couldn't get there fast enough. Their radar can't see the boat before the boat can hear the radar, and the boat's coastal command will soon be asked to catch the new Soviet nuclear ones, the first about to launch, don't snorkel at all. There will be no window of opportunity because there is no mast. No mast means no radar contact. No surfacing means no photograph. Whatever coastal command catches next will have to be caught while it's underwater by something other than a Shackleton. The crew land at first light, fill in the paperwork and go to bed. Little do they know that later that day in Westminster, a man named Sands will deliver a defence white paper that will reshape British military procurement for a generation, and the aircraft they've just flown isn't in it. Duncan Sands is Minister of Defence in Harold Macmillan's government, with a brief from the Prime Minister to cut British defence spending and rebuild the armed forces around a nuclear deterrent and missiles. His white paper, published on the 4th of April 1957 as a statement on defence, runs to just a few thousand words. The paper's central claim was that future wars would be fought entirely by missiles. Manned aircraft were on the way out. Sands announced the RAF was unlikely to require any new fighters or bombers and that work on those projects would stop. The Chief of the Air Staff is said to have remarked, "I wonder if I'll still be allowed to wear my wings." The 57 paper is one of the most consequential defence documents in post-war British history, and one of the most argued about. Even 60 odd years on, historians still can't agree whether it was clear-eyed reckoning with the cost of empire or cost-cutting dressed up as strategy. For the RAF, it lands as a kind of accountancy with cancellations, scaled-down requirements, programs folded into one another. Firms that build the aircraft for the RAF, it's a list of projects that will never be funded. For Coastal Command, it's business as usual. There's no Shackleton replacement project to cancel because there's never been one funded to start. Maritime patrol is not glamorous, and it's not perceived as central to the nuclear deterrent. The V-Force does that, Britain's fleet of nuclear-armed Vulcan and Victor bombers, the country's strategic deterrent, and so when the Sands cuts go through, the people writing the requirement for the next maritime patrol aircraft are not given a second thought. There was even a phrase for it inside the RAF, the Cinderella Service, a label that is older than the Shackleton. Coastal Command was given a title during the Second World War when its work in the North Atlantic, which was finding and killing U-boats, escorting the convoys that fed Britain, was overshadowed in the public eye by Bomber Command's offensive against Germany and Fighter Command's defence of the home islands. The maritime crews knew what they were doing mattered. They could see the tonnage figures of the enemy vessels sunk, but the publicity, the funding and the political weight went elsewhere. Coastal Command finished the war as one of the most effective anti-submarine outfits anywhere in the world, with 185 U-boats sunk by their aircraft by the official RAF count. But that had come at the cost of 6,000 aircrew lost over the North Atlantic. When the war ended, the Lend-Lease aircraft, the B-17s and B-24s that had given the command the range to close the Atlantic gap, went back to the Americans within months of VJ Day. The squadrons that flew them were disbanded. The aircrews who knew the work either signed on for short service commissions elsewhere in the RAF or returned to civilian life. By 1947, the command was flying Sunderlands and surplus Lancasters, and the planned Sunderland replacement called the Shetland had been cancelled. The shortfall was acute enough that in 1952 the United States lent Britain 52 Lockheed Neptunes with crews being trained in America. The aircraft were flown out of Kinloss and Topcliffe until 1956, when they too went back. Britain's maritime patrol force for those 4 years was operating on borrowed kit. Between 1945 and 1955, the Admiralty made at least 3 attempts to take Coastal Command off the RAF and bring it under their control. The argument was that maritime patrol was a naval function and that the fleet air arm should run it. Each attempt was beaten back and Coastal Command stayed with the RAF. With the V-Force protected, the fighter program being scaled back, the army being shrunk and the Treasury looking for savings everywhere else, a Shackleton replacement was just something to be talked about in the officers' mess over a round of beers. The Shackleton, in its system's view, was the aircraft Coastal Command had, and the aircraft Coastal Command had was the aircraft Coastal Command was going to keep. The first real attempt to do something about it came not from London but from Brussels. In 1958, NATO issued a common requirement for a long-range maritime patrol aircraft to replace the Lockheed Neptunes then flying with several European air forces. The idea was the standard NATO idea of the period: pool the demand across member nations, run a competition, build one aircraft for everyone and, of course, share the cost. Britain, being a member of NATO, was expected to be a customer and chip in. Britain's official position going in was that as a NATO member it would accept whatever aircraft the competition chose, though its private position was that it had plenty of time and wouldn't be bound by any NATO decision and would pursue a national solution if it preferred one. On the 21st of October 1958, NATO announced the winner, the Brigade BR-1150, later the Brigade Atlantique, a French twin turboprop powered by Rolls-Royce Tynes. But the air staff had already decided that the Atlantique wasn't what the RAF wanted: too small, too short-ranged, propeller-driven at the moment when the rest of the Air Force was going jet-powered. So they walked away from a program that would produce a working aircraft on a known timeline in favour of a national program that, 6 years later, would still not exist. What came next was half a decade of design studies. A.V. Rowe and Company, or Avro, had built the Shackleton at Woodford in Cheshire, and Avro was in 1957 the firm that the RAF expected would build whatever replaced it. Avro had a maritime tradition going back to the Anson and a working relationship with Coastal Command that went back further still. So when the question of a Shackleton replacement was first asked, Avro were naturally approached to produce a workable design. Their first proposal was the Avro 745, which was in essence a better Shackleton. 2 Rolls-Royce Dart turboprops, a stretched airframe with the same crew layout and the same broad mission profile. But the 745 didn't progress beyond the drawing board. By the time the 745 was abandoned, the British aircraft industry had been reorganised. AV became part of the newly created Hawker Siddeley Group in its Avro Whitworth division, with production at Shackleton and design at Woodford near Manchester. The design office at Woodford moved on from the 745 to a new study, the Avro 775. This design in outline looked very much like the Breguet Atlantique that Britain had walked away from, with two wing-mounted turboprops and a single Rolls-Royce Spade turbofan added in the tail to give it a higher dash speed. It too didn't progress beyond a drawing either. The 775 was then followed by the Avro 776. This would be a little bit more ambitious with swept wings and powered by three Rolls-Royce RB178 turbofans grouped at the tail, looking less like a maritime patrol aircraft and more like an airliner with sensors bolted on. 6 years of study work on 3 different configurations produced no aircraft at all. In the meantime, the men who flew the Shackletons through those 6 years were flying an aircraft that was being rebuilt around them. The centre section wing spar, the main beam running through the fuselage into which the wings were routed, was failing faster than the calculations had predicted. The engineers went back to the drawing board. They came back with a structural strengthening program, and when that wasn't enough, with another, and when that wasn't enough, with another. By the early 1960s, nearly all the Mark 1s, Mark 2s and the new Mark 3s with their redesigned wings, tip tanks and auxiliary jet engines tucked into the outer nacelles for takeoff thrust had been temporarily grounded while the engineers worked out the structural issues. The squadrons lost aircraft to the hangar for months at a time, but they got them back stronger, but not younger. Some of this was the aeroplane, some of it was, fair to say, the job. A maritime patroller spends most of its flying hours at low level in dense air over a sea that consumes airframe life faster than the design had accounted for. And by 1962, what it would be hunting was getting bigger, quieter and harder to find every year. 7 months before the procurement system would start down the road of producing the requirements that became the Nimrod, Harold Macmillan was in the Bahamas trying to save the future of the British nuclear deterrent. In early November 1962, the United States Secretary of Defense Robert McNamara recommended to President John F. Kennedy that the United States cancel Skybolt, an air-launched ballistic missile the United Kingdom had been planning to buy and fit to the V-Force. The V-Force, the Vulcans and Victors, were at the time armed with free-fall thermonuclear weapons, meaning they had to fly into enemy territory and close to or over the target to drop their bombs. But their working lives had a fixed endpoint. By about 1965, Soviet surface-to-air missile defenses were expected to make manned penetration of Russian airspace impractical. But with Skybolt fired from outside their airspace, it was thought they could push the endpoint out to the 1970s. Without Skybolt, the V-Force would be left with Blue Steel, a shorter range weapon that put the bombers within range of Soviet missiles. Blue Steel bought a few more years, but it did not solve the problem. The way the Americans handled the cancellation was almost worse than the cancellation itself. McNamara contacted the British ambassador in Washington on the 8th of November and the British Minister of Defence Peter Thornycroft on the 9th, with the same story each time: probable cancellation, no decision made yet. What the Americans hadn't said in any of those conversations was that the decision had already been made. Britain had spent 10 years calling itself a nuclear power on its own terms. Its own weapons, its own bombers, and more importantly, its own finger on the trigger. Take the V-Force away in 1965 with nothing behind it, and Britain was either out of the nuclear business or in it on American terms. Neither was survivable politically. Macmillan needed something to buy. And since nobody else was building anything that worked, it had to be American, but it had to look British enough to be able to sell at home. And it had to be ready before the V-Force ran out of credibility. So Harold Macmillan and his delegation flew out to the Bahamas on the 18th of December to negotiate with the Americans. The meetings with President Kennedy were tense. Lord Home, the British Foreign Secretary, thought the government might have fallen if Macmillan had come home with nothing. Kennedy opened by offering to keep Skybolt going. The Americans would pick up the $100 million of further development costs, Britain would pay the rest and keep the missiles she had already ordered. Macmillan refused. Skybolt had been too publicly discredited in the British press to be politically saleable. He says, while the proposed marriage with Skybolt was not exactly a shotgun wedding, the virginity of the lady must now be regarded as doubtful. Kennedy then offered Hound Dog, a supersonic air-launched nuclear-armed cruise missile. Macmillan turned that one down too, because he wanted Polaris. Polaris was an American program, a solid-fueled ballistic missile that could be launched from a submerged submarine. The US Navy had been working on it since the mid-1950s, and by the end of 1962 it was in service. What Polaris had that no British weapon had and no other delivery method came close to was that it was effectively impossible to find before it fired. A V-bomber sat on a runway. A land-based missile sat in a silo. Both could be destroyed by a preemptive strike if the other side knew where they were. And the other side, in 1962, increasingly did. However, Kennedy didn't want to give Polaris to the British. Polaris was, in Kennedy's words to Macmillan, an entirely different matter from Skybolt, a submarine-launched ballistic missile considerably more capable than the missile being cancelled, with a service life expected to run into the 1980s. After several days of vigorous argument, the meetings produced an agreement Macmillan considered the best he was going to get. Britain would build the submarines and the Americans would supply Polaris. The agreement was published on the 21st of December and Skybolt was formally cancelled the day after. The deterrent had been the RAFs. They had wanted to keep Skybolt and keep that role, but they lost. The job was now the Royal Navy's. So bombers, missiles, submarines and a Prime Minister in the Bahamas, what's any of this got to do with Coastal Command? Well, a Polaris boat is invulnerable provided nobody knows where she is. 16 missiles somewhere in the Atlantic where nobody can find. A boat the Soviets can find stops being a deterrent and becomes a target, which makes the Soviet submarine that finds her the most important military asset in the world. Somebody had to find those submarines first, and the submarines that mattered in 1962 were the ones the Soviets had been building for the past 5 years. Stalin had wanted a battleship navy, cruisers and capital ships, the kind that put Russia at the top table of world affairs. His successor, Nikita Khrushchev, had no intention of spending Soviet money on ships built to fight the last war, when the war he was worried about would be fought by aircraft carriers and submarines. In 1956, he appointed Sergei Grushkov to run the Navy. Grushkov was 45, the youngest commander-in-chief the Soviet Navy had ever had, and he would hold the post until 1985. He didn't start from a blank slate. The yards had been turning out conventional submarines since the end of the war, and the Northern Fleet at Severomorsk already had a force of them, most of it tied to coastal defense, but a fraction of the Soviet underwater strength. What Grushkov changed was what the force was for. He set about turning a fleet built to guard the Soviet coast into one that could fight in the Atlantic and sink American carriers before they came within range of it. And Khrushchev had no intention of keeping the strategy quiet. At a Royal Navy College dinner in Greenwich in April 1956, on a state visit to Britain, he stood up in front of his hosts and told them their country had ruled the waves, but that was a thing of the past, and in any future war, he said, the chief naval weapon would be the submarine. It was the diplomatic equivalent of standing up at somebody else's dinner table and telling them their profession no longer existed. In his memoirs, he recalled how he and Grushkov had decided to put submarine construction literally on an assembly line. The conventional boats came first. The Whiskey class had begun appearing in 1951, a Soviet design owing a substantial debt to the German Type 21, and the run eventually ran to more than 200 hulls. The Zulu followed in 1952, longer range and built around a proper snorkel. The Foxtrot came at the end of the decade, the ocean-going diesel boat that the Nimrods would still be tracking in the Mediterranean 25 years later. The intelligence services claimed that by 1966 the Soviet Navy had 350 conventional submarines and 50 nuclear-powered ones. Across the same period, the Royal Navy was building boats in single figures. And these were the boats, the diesel ones, that the Shackleton was built to catch. A diesel submarine can't stay submerged indefinitely. Its batteries run down and the air in a boat becomes foul. Every few hours the boat has to come up to periscope depth, push a snorkel mast above the waves and run its diesels to charge its batteries and refresh the air. The snorkel is a narrow steel mast, not much more than a pipe. It puts very little above the waves and it isn't up for long. For the boats of the late 1950s it would be up for a couple of hours. That was the Shackleton's window of opportunity to find that sub. And the aircraft carried the ASV-21, an air-to-surface radar set originally developed from the wartime H-2S set. Against a surface ship, it could pick out a destroyer at 80 miles. Against a snorkel mask, a steel pipe a few inches across, sticking up perhaps a few feet above the waves, it could manage about 10 miles in flat seas and much less than that in anything else. The submarine, meanwhile, carried a radar warning receiver that could pick up the Shackleton's radar transmissions at considerably greater range than the radar could detect the mast. So the Shackleton's crew used the radar sparingly in short bursts, sometimes sweeping it behind the beam of the aircraft, hoping to catch the boat with its mast up before the boat could pull the mast back down. A Shackleton navigator described it as a cat and mouse on top of looking for a needle in a haystack. Against the original Whiskey-class tubs, in a moderate sea, the aircraft still held its own. The problem was not the quality of the boats, the problem was the sheer quantity of them. With over 300 hulls in the Soviet inventory and rising, even an aircraft that worked was going to be swamped by the geometry of searching millions of square miles of water in the North Atlantic. The number of Shackleton hours available to search it was finite and falling, and the Cinderella Service's share of the defense budget was not about to grow. Then, on the 9th of August 1957, the Soviets launched K3, the first of the Project 627 class, their first nuclear submarine, given the NATO designation November. Despite being rushed into service in July 1958, her published submerged speed was 30 knots, fast enough to outrun every surface escort in the Royal Navy, and her propulsion did not depend on coming up to charge anything. She could leave Severomorsk submerged, transit the Norwegian Sea at depth, and arrive in the open Atlantic, having given the Shackleton nothing to find. In a 1958 meeting in Moscow on the future of the Navy, Nikita Khrushchev and his Commander-in-Chief Gushkov set the target for a new fleet: 70 ballistic missile submarines, 60 cruise missile submarines, and 50 attack boats. The November design was further reworked into two more classes: the Hotel variant, a ballistic missile boat carrying 3 missiles on its sail, and the Echo, a cruise missile boat designed to kill American carriers from over the horizon. The Americans had seen this coming. Through the late 1950s, the US Navy had been laying hydrophones on the floor of the North Atlantic, a system called SOSUS, Sound Surveillance System, which could pick up the radiated noise of a Soviet submarine the moment it crossed one of NATO's listening lines. The first arrays were activated in 1961. By the summer of '62, SOSUS had detected the first Soviet diesel submarine, then its first nuclear one in the waters north of Norway. SOSUS could tell you a Soviet boat had crossed a listening line, not where it had gone after that. What it produced was a probability box, sometimes 3,000 square nautical miles of ocean, sometimes more, inside of which there was a Soviet submarine somewhere. Converting that probability box into a specific position needed something that could fly to the box, lay a sonobuoy field, process the acoustic returns on board, and pin the boat to a point. Something fast enough to reach the box before the boat had moved out of it, with enough internal volume to carry the analog computers that would make sense of what came back through the hydrophones. That something was what Britain didn't have. From December 1962 onwards, that was no longer affordable. The Macmillan and Kennedy Polaris deal had handed the deterrent to the Royal Navy, and the Royal Navy was now building 4 ballistic boats to carry them: Resolution, Repulse, Renown, and Revenge. 2 were being built at Vickers in Barrow and 2 at Camel Laird in Birkenhead. Resolution herself had been ordered on the 21st of May 1963, 6 months after Macmillan came home from his meeting with Kennedy, and her keel was laid down at Barrow in February 1964. Each boat would carry 16 Polaris missiles in vertical tubes behind the fin. 4 boats was the minimum number that would give Britain what the Admiralty called continuous at-sea deterrence. 1 boat on patrol, 1 working up to relieve her, 1 in maintenance, 1 in deep refit. Take any one of those away and the cycle broke. Take the patrolling boat away and the deterrent broke with it. Resolution, the first of the boats, was expected on her first deterrent patrol by the middle of 1968. That gave the air staff 5 years. 5 years to replace an aircraft conceived in 1944 with something that could find a Soviet nuclear submarine in the open Atlantic, at the moment when the Soviet submarine fleet stood at many hundreds and growing. To anybody looking in, it seemed it would be unbuildable in any reasonable timescale. If you're still with me, thank you. Here is Winnie the rabbit having a slice of apple for her tea. If you would like to feed the algorithm, a like genuinely helps the video find other people. Also, let me know in the comments which aircraft you want covered next. Right, back to the story. In July 1963, the Air Staff issued a document that was supposed to start fixing the problem. Numbered Air Staff Target 357, it was the system's first serious attempt to specify the aircraft Coastal Command was going to need. Though an Air Staff target is not a requirement, it's the step before one, a statement of what the operators want the next aircraft to do, in broad capability terms against which the design studies and the eventual specification will be written. Air Staff Target 357 laid out the wish list for a long-range jet aircraft with an integrated weapons system capable of meeting the worst foreseeable treatment from the Soviet Navy by about 1970. It was in the description of one of the officers who had to work with it, an all-singing, all-dancing aircraft to be built from scratch, costing an enormous amount of money at a time when there wasn't much of it about. The airframe required to carry them on the scale envisaged would need a clean sheet development program of the kind the procurement system had spent years failing to fund. The officer who inherited it was Group Captain Hugh Eccles. Eccles was the Deputy Director of Operational Requirements at the Air Ministry, the office that wrote the specifications the RAF's next aircraft would be built against, with responsibility, amongst others, for the Shackleton replacement. When Eccles read the target, he understood more or less that it would have to be torn up. What Eccles did next, before the system formally admitted that AST-357 was unbuildable, was an experiment. He borrowed the prototype VC-10 from Vickers. The VC-10 in late 1963 wasn't yet in BOAC service. Sir George Edwards' Airliner had been designed for hot and high African and Asian airfields, with 4 Conway turbofans grouped under a tall T-tail. Vickers had built one prototype that was still carrying out test flights. Eccles managed to get his hands on it and took it up to 25,000 feet over the south coast of England and asked the pilots to fly it in the way a maritime patrol aircraft would have to be flown. That meant diving a 4-engine jet airliner down to 500 feet above the sea off the Isle of Wight. 500 feet is practically wave-top altitude. It's also the altitude at which a large jet airliner is a long wave where the handbook says it should be. The Conways were designed for transit cruise at altitudes around 40,000 feet, not dragging through dense low altitude air with the throttles balanced to hold 500 feet over a moving surface. The airframe had also been designed to absorb gust loads at cruise weight, not the bumpier work at low level over the sea. Eccles was asking the VC-10 to do both, one after the other, for the duration of a notional patrol. They climbed back up to 25,000 feet and dived again and spent an afternoon at it. What Eccles wanted to know was whether the swept-wing jet airliner, any of them, the VC-10 was just one that he could lay his hands on, could fly the maritime patrol profile without its airframe or its handling complaining. By the end of the afternoon, his answer was yes. The aircraft had absorbed the dives, had handled at 500 feet and obviously had climbed back up. The concept was, in Eccles' judgment, perfectly feasible, and the VC-10 was absolutely the right aeroplane. But despite being the right aeroplane, the system did not order the VC-10. It went instead through one more round of paperwork. While Eccles was diving the VC-10 over the Isle of Wight, the design office at Hatfield was drawing up the aircraft Hawker Siddeley intended to put up against AST-357. Hatfield had a lot of history here. The former de Havilland team had been working on Trident-based maritime studies since the late 1950s, back when the original DH-121 Trident airliner had been designed around 3 Rolls-Royce RB141 Medway turbofans, a bigger engine and aircraft with the range to do useful work over the Atlantic. It's been said that if either the Hatfield Trident-derived maritime patrol aircraft or the Avro 776 had been pushed quickly into development, a British narrow-body jet maritime patroller could have been on the world market by the early 1960s, preempting the Boeing P-8 Poseidon by 40 years. The Trident that Hatfield is in place of the Medways. The Trident that emerged from BEA's specification was an aircraft optimized for short European sectors, and an aircraft that surrendered the world short-haul market to the Boeing 727 the moment it was built. Hatfield and the Woodford teams between them studied it anyway. The proposal was designated the HS-800. Hawker Siddeley submitted the HS-800 to the Air Staff in April 1964 regardless, but it was inadequate from the outset, an obvious non-starter. What was bizarre about it, looking back, was how nearly right it had been. In late spring 1964, the Treasury refused to fund AST-357 as written. The bid prices were too high and the requirement was frankly unaffordable. The Air Staff was sent back to write something cheaper. On the 4th of June 1964, it issued Air Staff Requirement 381. Where AST-357 had asked for a clean sheet jet capable of meeting the worst foreseeable threat by 1970, ASR-381 asked for a less advanced aircraft, justifiable against the Breguet Atlantique the French were already flying, with as much of the Shackleton's existing equipment carried across as possible to save money. The Air Staff's own account afterwards was that the reuse-based answer had been theirs. Either way, the result was the same. ASR-381 required an aircraft in service by 1968, and an aircraft in service in less than 4 years was not going to be designed from scratch. The shortlist of what the procurement system was in a position to take ran to about a dozen aircraft. The French Breguet Atlantique was the obvious reference point, a clean sheet, purpose-designed maritime patroller. The Lockheed P-3 Orion was the American answer, 4 Allison turboprops already in service with the United States Navy. The British submissions were a mix of existing airliners and freighters reworked for the maritime role. There was the BAC 1011. This was a 111 fuselage with VC-10 wings stitched on. Also fast and slow versions of the Belfast freighter, and of course the VC-10 itself. Some studies envisaged mixing turbofan and turboprop propulsion. Others looked at variable geometry as the way of solving the issue of high dash speeds to get to a contact and the low speed loiter requirements that the maritime patrol needed. During all of this was an airframe nobody had a use for. The de Havilland Comet 4C had been on sale since the late 1950s. It was the longest ranged of the Comet 4 family. The high capacity fuselage of the 4B mated to the wing of the Comet 4. It was, in commercial terms, late. BOAC had committed to Boeing 707s for their long-haul routes, and the major flag carriers had gone the same way or to the DC-8, and only 30 Comet 4Cs were ever built. 23 of them had been assembled at the de Havilland factory at Harden near Chester, and had been sold to Mexicana, Sudan Airways, Aerolíneas, Kuwait, the RAF as a transport, and a Saudi King. But 2 hadn't sold at all. Both sat at Chester, unfinished, while their builder belonged to the same operation as the firm that was now writing a maritime patrol bid. Hawker Siddeley had absorbed de Havilland in 1960 and AV Row in 1963. The Comet pressure hull was by 1964 a Hawker Siddeley asset. What the Comet had that the design studies on the drawing boards didn't have was that it existed. Not only that, but the aircraft was flying and its tooling was paid for. The pressure hull's troubles, which had claimed 2 aircraft in 1954 and almost ended the type 10 years earlier, had been solved in a program of structural rebuilding that had cost de Havilland the world airliner market and produced, at the end of it, one of the most reliable passenger aircraft anyone had built. The Comet 4 family had logged more than 1.5 million hours by the time the Shackleton replacement bids were being written. Gilbert Whitehead, Executive Director and Chief Engineer of the Avro Whitworth Division at Woodford, took the decision to base the bid on a modified Comet 4C in about a week. Whitehead had worked through the studies and the requirement against the timescale and the cost ceiling, and concluded that nothing else fitted. The Comet 4C had the payload to carry a maritime crew and their equipment. Its wing loading gave it both a healthy dash speed and the ability to loiter at minimum speed. 2 airframes were sitting at Chester that could be converted into prototypes without having to start a new production line. The basic rule Whitehead set the bid team and held them to was minimum change from the Comet 4. The aircraft would have a new nose large enough to house a search radar. Underneath the fuselage would go an unpressurized pannier for weapons, sonobuoys and droppable dinghies. The pressure hull would be isolated from the pannier so the basic Comet structure didn't have to be recertified. A long tail boom in the rear would house a magnetic anomaly detector, a device that runs a magnetic anomaly detection track and sensitive enough to pick up the distortion that a submerged submarine makes in the Earth's magnetic field as the aircraft flies overhead. And Rolls-Royce Spey turbofans would replace the Comet's Avon turbojets, because the Spey burned less fuel and gave the aircraft the endurance the air staff was asking for. The reasoning Whitehead applied was financial as much as engineering. Any change from the Comet 4 baseline cost time, and time costs money, and the contract, if there was going to be one, was likely to be unforgiving on both. By July 1964, the Hawker Siddeley team at Woodford, supported by the former de Havilland designers at Hatfield, had a detailed proposal, and it carried the manufacturer's designation HS801. To keep costs further down, the bid specified that much of the electronics fitted to the Shackleton would be carried across to the new aircraft. The avionics inheritance was, on the bid team's reading, what made the timescale credible. On the 2nd of February 1965, the Labour government, in office since the previous October under Harold Wilson, announced in Parliament its intention to order a maritime version of the Comet 4C to replace the 60 Mark II Shackletons still in service. The decision was sharply criticised. The main critic was Hugh Fraser, the Conservative member for Stratford and Stone, who had been Secretary of State for Air in the previous government, the office in which AST 357 had been written. Fraser called the Comet decision nonsensical, and the charge had something in it. The maritime version of an airframe whose own commercial life was winding down, fitted with electronics taken from the aircraft it was replacing. It was not the all-singing, all-dancing aircraft his own air ministry had specified 2 years earlier. It was also, by implication, a defence of the specification he had supervised, a specification which the system had now formally abandoned for being unaffordable and unbuildable in the time available. The Atlantique still wasn't what the RAF needed. The Orion was American. The clean sheet designs were either not going to be ready in time or not going to be affordable when they were. The HS801, against those constraints, was the answer the constraints permitted. In June 1965, Hawker Siddeley received the formal instruction to proceed, and in January 1966, the contract was signed. The contract was for 38 production aircraft at a fixed price of £96 million, and it was unique in 2 ways. It was the first large fixed price contract a British government had placed for a military aircraft, and the first Hawker Siddeley had ever undertaken. The programme dates were defined. If the aircraft slipped, the company carried the cost. The same were true if the unit cost went up. The fixed price clause transferred a large slice of procurement risk from the customer to the contractor, a risk transfer the Treasury was, by 1966, increasingly determined to push through on major aerospace work, and one Hawker Siddeley took on in the knowledge that getting it wrong would be expensive. What Avro had that gave their management the confidence to accept the risk was the Avro 748, a small civil airliner the company had developed entirely off its own bat against critical customer timescales and which had first flown in 1960. The 748 program had taught Avro that a company-funded aircraft with defined delivery dates could be run to those dates if the design discipline was held. The Nimrod contract was an order of magnitude larger, and the customer was the Air Ministry rather than a regional airline. But the management position was the same. Hold of a design, don't change anything that didn't have to be changed. To Tony Blackman, Avro's deputy chief test pilot at the time, wrote later that the contract was a success, quick by Ministry of Defense procurement standards, fixed price, defined program, and accepted by a company that knew how to deliver on company-funded timescales. The contract requirements on that timescale and budget meant that the airframe carried compromises from the start. Shackleton avionics in the 1960s airframe, a 16-year-old pressure hull, a cost squeeze that closed off proper optimization for the maritime role. What counted as success here depended on where you were standing. Now the announcement had been made, the design office had to start turning a bid document into a working aircraft. The Comet had originally been a de Havilland aircraft with the design team at Hatfield and production at Chester. After the Hawker Siddeley absorptions, all of the HS-801 work came under the Avro Whitworth umbrella, and henceforth the centre of gravity of the programme was at Woodford, and it wouldn't be long before Whitehead acquired the nickname Mr. Nimrod. Conversion work on the first development prototype that became X-Ray Victor 148 began at Chester early in 1965. Because the airframe had not been fully assembled when the project began, the SPAY engines could be installed from the outset and became the handling and performance prototype. The other airframe, further along, became X-Ray Victor 147. It kept its A1 engines, fitted instead with the new avionics and a magnetic anomaly detector boom in the tail. The man running the Nimrod project at Woodford was R.G. Dick Proudlove, the project manager. Proudlove had come up through the Avro design tradition, and his job through 1965 and 1966 was to convert a 16-year-old civil airliner into a maritime patrol aircraft without breaking either the airframe or the timescale. Years later, Proudlove would say that there were really very few fundamental problems in the design work itself. The essential element, the thing the whole shape of the aircraft turned on, was the pannier, the unpressurized weapons bay that would hang underneath the Comet fuselage. The pannier's dimensions were determined by what the RAF needed to put inside it. Its shape was determined by basic aerodynamic principles. Everything else, Proudlove said, followed logically and quite quickly. What the RAF needed inside it was a search radar scanner, a Doppler navigation bay, sonar buoys, droppable air-sea rescue dinghies, mines and torpedoes, and the room to add a more capable radar when one became available. The radar that would actually be fitted was the ASV-21, a set originally supplied for the Shackleton, with a scanner sized for the Shackleton's radome. The pannier had to house it and the scanner that would replace it. Proudlove and his team sized the pannier accordingly, large enough for the radar they had, large enough for the radar they thought was coming, and large enough for everything else the operators wanted to load into a maritime aircraft. The aerodynamic principle was simpler. A bulge under a swept wing jet has to be a fair shape, or the drag will eat the range. The pannier was given the deepest belly the Comet's wing fuselage geometry could carry and fared forward and aft into the lines of the original fuselage. From the side, the result was a fuselage with two distinct rounded sections, one above the other, the original Comet pressure hull on top and the pannier hanging below. The aircraft picked up its first nickname from the shape, the double bubble. The engineering problem inside the shape was harder. The pannier was unpressurized. The fuselage above it was pressurized to the design figure for the Comet pressure hull, 8¼ pounds per square inch, roughly double what any previous airliner had carried, which was what flying at high altitude required. The hull in the form it had taken after the 1954 rebuild was by 1965 one of the most thoroughly tested pressure structures in civil aviation. The solution was to attach the pannier to the fuselage in segments, a series of separate sections rather than a single rigid box, so that load changes the pannier picked up in flight through turbulence, weapons bay doors opening, weight shifts as stores were dropped, couldn't be transmitted into the pressure hull above. The pressure hull stayed isolated from what was happening underneath it. That kept the Comet certification basis intact, which kept the contract deliverable. The Comet pressure hull was the part of the aircraft nobody at Woodford wanted to touch. Two Comet 1s had broken up in flight in 1954 because the cabin had been pressurized through enough cycles to fatigue crack the corners of the square cabin windows. De Havilland had spent the rest of the decade rebuilding the type around oval windows and the strengthened skin. By 1965, the Comet 4 hull was one of the most thoroughly tested pressure structures in civil aviation, and the rule inside the design office was that anyone cutting a new hole in it was carrying the weight of that history. The Nimrod cut several. Two of them were in the cockpit. The pilot's windscreen was deepened for better view at low level, and the pair of small windows above it, the eyebrow windows, let the pilots look up when they were making tight turns during the search profile. Each new pane naturally was pressure tested before it was cleared to fly. There was one other shape change at the fuselage level. 6 feet of fuselage were cut out of the airframe ahead of the wing, a single bay removed in conversion. The reasoning was directional stability. The deeper forward fuselage created by the new radar nodes would push the aircraft's keel area forward, and a shorter fuselage would help the rudder hold authority against it. Whether that worked, the flight test would have to say. By late 1966, with both prototypes nearing first flight, the Woodford team had run wind tunnel work on the question, and Whitehead's office had already drawn up a larger dorsal fin in case the existing one proved marginal. Drawn but not yet fitted. The Comet 4 had been built around the Rolls-Royce Avon, a turbojet developed for the Canberra in 1950 and fitted afterwards to the Hunter, the Lightning and the Valiant. By 1965, a mature engine with a long service record. In its Mark 525 form, fitted to the Comet 4C, the Avon was rated at 10,150 pounds of takeoff thrust and burned fuel at a specific consumption of 0.87. The Nimrod was to be built around the Rolls-Royce Spey Mark 250. The Spey was a turbofan rather than a turbojet, an engine with a fan at the front that pushed cool air around a hot core instead of through it. Civil and military versions of the Spey were maturing fast in 1965, which meant the engine would inherit improvements paid for elsewhere. For a maritime patrol aircraft, there were two numbers that really mattered. Takeoff thrust on the Mark 250 was initially 12,140 pounds, eventually cleared at 12,500, and the specific fuel consumption at takeoff rating was 0.58. 2,000 pounds more thrust per engine and a third less fuel burn for the same work. The Spey was also shorter than the Avon, 117 inches against 134, and lighter, even with the alternator the Nimrod's avionics power demand required. The shorter engine fitted more easily into a Comet engine bay, plus the lighter engine exerted less load through the wing root mountings. The geometry of the engine bays needed only modest modification, mostly to open them up vertically for the bigger engine ducts and to strengthen them for the higher thrust. The Comet wing kept its inboard engine layout, with all 4 engines clustered close to the fuselage centerline, and this had a useful side effect. On a 4-engined aircraft, if you lose an engine on one side, the remaining engines on the other side push the aircraft into a turn. The pilot has to counter the turn on the rudder pedals. The further out from the fuselage the engines are mounted, the harder the rudder has to work, and on a 707 for example, with engines hung out on long pylons, asymmetric flying is heavy work. On the Comet, with its engines tucked in close to the fuselage, asymmetric flying was light on the pedals. That mattered since the proposal Whitehead's team had made was that the Nimrod would extend its time on station by shutting down the engines during the search, flying first on 3, then on 2, restarting the others when needed for the transit home. The fuel saving would more than compensate for the specific fuel consumption disadvantage the turbofan had been argued to have against the turboprop of the Breguet Atlantique. The aircraft would have the dash speed of a jet and something close to the loiter economy of a propeller aircraft. To make that work, the engines had to start in the air reliably and repeatedly. The Spey's air turbine starter needed a source of compressed air, and the source had to be the other engine still running. The design solution was a cross-feed air duct running through the airframe, a pipe that could route bleed air from one engine to another starter on either side of the aircraft, so that any engine could be restarted from any other. The other engineering job in the Spey's was marinization. A maritime patrol aircraft spends its life at low altitude over salt water, and salt atmospheres are not long-term friends with most aircraft metals. The Spey 250 had to be coated throughout with anti-corrosive treatments and aluminium-based protective finishes, while magnesium alloys, which corrode aggressively in marine conditions, were excluded entirely from the engine. For an aircraft that would do most of its flying alone over the North Atlantic, noise was not an issue. So the jet nozzles were left as plain tubes, sized for propulsive efficiency rather than acoustic suppression. The basic civil Comet 4 fuel system carried over almost unchanged. Integral tankage in the wing, the same redux bonded structure de Havilland had pioneered on the original Comet, using metal-to-metal adhesive bonding in place of much of the riveting that conventional airframes relied on. To that, the Nimrod added new keel tanks in the lower fuselage, raising total internal fuel to just under 11,000 imperial gallons. For ferry flights, 6 additional tanks could be loaded into the weapons bay, taking the maximum fuel load to roughly 100,000 pounds. The fuel alone on a Nimrod ferry flight weighed almost as much as a Comet 1, fully loaded with passengers, crew and its own fuel at maximum takeoff weight. The long tail extension on every production Nimrod housed the system the aircraft's whole final attack geometry was built around, the magnetic anomaly detector. The physics was straightforward and slightly preposterous. The Earth has a magnetic field. At the latitudes the Nimrod would be working, the Earth's field runs at roughly 50,000 nanotesla, a strength the human body never notices, but one a sufficiently delicate instrument can measure to a fraction of a nanotesla, down to 1 part in 50,000. It's the equivalent of standing at one end of a football pitch and noticing the ball has moved 2 millimeters. A submerged submarine is a few thousand tons of ferrous metals moving through that field, and it distorts the field locally. The distortion is small, and dependent on the boat's depth, its orientation, the material of its hull, and the degree to which it had been degaussed to reduce exactly this kind of detection, the anomaly might be 1 nanotesla, sometimes less. 1 part in 50,000, that was the signal, and the sensor they had to pick this up was an Emerson ASQ-10A, and it was supplied as a complete unit and bolted to the end of a long boom for one reason. The aircraft carrying the sensor itself was a large piece of metal full of moving electrical currents, ferrous fasteners and 4 turbofan engines, and its own magnetic field at the fuselage was orders of magnitude larger than anything a submarine would produce. The boom held the sensor far enough behind the aircraft that the aircraft's own signature, while still present, could be subtracted. And subtracting it was the job of a separate piece of equipment built by Canadian Aviation Electronics called the 9-term compensator. The compensator measured the aircraft's own magnetic moment on 9 separate axes and removed it from the signal coming back from the sensor. What was left in principle was the field outside the aircraft, though what was left in practice was an aircraft-shaped piece of noise that the operator had to learn to read through. The output appeared as a paper trace at the ESM's operator station in the cabin, a flat line most of the time. When the aircraft passed over a submerged submarine, the trace twitched. The callback through the intercom was the same one anti-submarine aircraft had been making since the system was invented in the Second World War. Mad Mark. The aircraft had to be almost directly over the boat. Detection range was a few hundred feet to a couple of thousand, depending on geometry. You didn't search with MAD, you used it last. The radar had found a contact and lost it. The sonar boys had narrowed the contact to a patch of ocean a few miles across and said something down there was making submarine noises. MAD was the instrument that said, yes, there's a submarine and it's here. Accurate enough to drop a torpedo on the mark alone. The cockpit of the new aircraft would have been immediately familiar to a pilot of a wartime Lancaster. The flight engineer at his station behind the pilots was responsible for fuel, engines, hydraulics and air conditioning. No multifunction displays or central computer feeding the instrument panel, just dials. The air staff had agreed that in the cockpit the basic flying instrumentation would be a Comet 4 with the latest Smith's automatic flight system fitted, and very little else would be changed. How exactly the pilots up front would talk to the crew working in the back of the aircraft was a question the bid team had left for later. The actual work, the bit that the aircraft existed to do, happened behind the cockpit in the main tactical compartment. Two navigators sat side by side, one handling routine navigation and the other handling the tactical picture. A radar operator, a communications officer and the sonar buoy operators were ranged around them, each of them with their own console. The kit on those consoles was what the contract could afford. The radar was the ASV-21 lifted straight across from the Shackleton. The routine navigator's plotting table was driven by an electromechanical computer that projected the aircraft's present position onto the chart he had spread out in front of him. The tactical navigator had something more ambitious to work with, a Marconi Elliott navigation and attack system built around the 920B, a digital computer whose 8 kilobytes of memory was in 1965 genuinely impressive. He could couple the 920B to the autopilot and from his seat at the back fly the aircraft in the horizontal plane. The diesel exhaust sniffer was the most ridiculous piece of kit on the aircraft and the most representative. It was called Autolycus after the Prince of Thieves in Greek mythology, who could steal anything and a master of stealth and deception. The sensor was an air sampler mounted in the roof of the flight deck, and what it sampled for was the hydrocarbon signature of diesel exhaust. The theory was straightforward. A Soviet diesel submarine, when it surfaced or snorkeled to charge its batteries, ran its engines. The engines vented exhaust into the air. The exhaust was a chemical signature that hung over the sea downwind of the boat. An aircraft flying through that signature could detect it, turn upwind and follow the trail back to the source. What the theory hadn't accounted for was every other diesel engine in the North Atlantic. Merchant ships and fishing trawlers also ran on diesel. The exhaust trail of a Soviet submarine that had snorkeled 3 hours earlier was indistinguishable from the exhaust trail of a Greek freighter that had passed through the same patch of water yesterday. The false alarm rate was, in the words of one Shackleton crews who used it, much too high for effective operational use. In practical terms, the system could struggle to distinguish a Soviet submarine from commercial shipping, fishing fleets or half the North Sea ferries on a busy afternoon. By 1965 the air staff knew this. The serious threat the boat's Polaris would need protecting from were the new Soviet nuclear submarines. The Novembers, the Hotels, the Echoes, nuclear submarines that didn't burn diesel. They didn't have the service to charge and therefore did not exhaust hydrocarbons. The sensor was useless against any of them before it was even fitted. The Nimrod got Autolycus anyway. It was on the equipment list, it had been carried across from the Shackleton under the contract's reuse clause, and the contract had been priced on the assumption that it would be installed. So it was installed, bolted into the roof of the flight deck of a brand new jet maritime patroller designed to hunt boats it could never detect. On early Nimrods, the Autolycus indicator at the navigator station that would have alerted a contact never lit during the aircraft's working life. The system was removed on the Mark II conversions and later with no operational regret. Autolycus is the single piece of kit that explains the whole compromise. The air staff knew the threat was changing. The contract though had been written before they knew how fast. Bill Gunston's reading of that years later was that the aircraft had been compromised before it flew, designed to be gutted and re-equipped almost as soon as it entered service, with heavy demands on its aircrew in the meantime. Tony Blackman, Hawker Siddeley's deputy chief test pilot during the bid, took a different view. Compromise hadn't been forced on the bid team had chosen it. It's safe to say that in 1965 a Nimrod with fully digital avionics wouldn't have been built at all. See TSR-2. By late 1966 the work share across the Hawker Siddeley factories had settled. Chester kept making the wing centre sections, modified now to take the space, and later took on fuselage sections and outer wings. Hatfield, the original Comet design home, made tailplanes and engine intakes. Shackleton, the old Avro factory, made the assemblies that were particular to the HS-801. Everything came together at Woodford, where individual airframes came off the line differing from each other in length and width, and where parts were not always interchangeable between aircraft. Hawker Siddeley took weapon system integration in-house too, unusual for the British aerospace industry for the period, which had tended to push that kind of work back onto the customer. By the end of 1966, X-Ray Victor 147 and X-Ray Victor 148 were at an advanced conversion stage, either awaiting their engines or being fitted out with avionics, and both aircraft would be ready to start flight testing the following spring. What the aircraft actually was when it flew depended on what the test program would find, and who was telling the story afterwards. X-Ray Victor 148 lifted off the runway at Harden on the afternoon of Tuesday the 23rd of May 1967, with John Cunningham in the left-hand seat and Jimmy Harrison in the right. The first Nimrod was airborne, a positioning hop between Hawker Siddeley's Chester plant, a de Havilland factory, and Avro's Woodford plant, where the rest of the test program would be run. The crewing was a piece of senior management arithmetic. Cunningham was de Havilland's chief test pilot and Harrison was Avro Whitworth's. It was a sort of compromise rather than a judgment of capability. Harrison would run the substantive testing afterwards. The maiden flight, an hour and 24 minutes, ought to have been Harrison's by right or wrong, but Cunningham's 18 years on a Comet and the simple political weight of the man in British aerospace put him in command and put Harrison in the right-hand seat. There's a photograph of the crew on the apron at Harden before they boarded. 7 men in a line. Bob, Dixon, Stubbs the navigator, Harrison, Cunningham, the flight engineers Haddock and Palmer, and the flight observers Johnson and Poole. They took X-Ray Victor 148 through basic handling across the speed range. They went through the stalling procedures, checked the engines, watched the system temperatures, and ran the pitot-static work the new radome geometry was going to need before the airspeed indicators could be trusted at low level. The wind tunnel work was proved right inside a month. A larger dorsal fin had been drawn up by Whitehead's office the previous year and sat on a shelf at Woodford waiting to see whether it would be needed. It was. The fin was fitted to X-Ray Victor 148 in June and to X-Ray Victor 147 before its first flight. On a clean sheet aircraft, the finding would have generated paperwork and a phase of slipping schedules. Because the modification already existed, the aircraft was back in the air that month. Then they found something else. The bigger fin had fixed directional stability in normal cruise, but opening the weapons bay doors in flight made it worse again. The pannier with its doors open had added more keel area aft than the design office had expected. The 6 feet of fuselage had been cut out ahead of the wing during conversion, taken out to push the keel area aft and give the rudder more authority, had been overcorrected. Now they needed some of it back, and the 6 feet was gone, so the crews had to simply learn to fly the aircraft accordingly. The other handling problem the test program found in the first weeks of flying was that the ailerons had a lot of friction and a lot of backlash. Slop in the cable runs, free play before the control surfaces actually moved. The aileron controls were the same cable and pulley system that Comet 4 had used. Control inputs at the column ran through a chain of cables and pulleys back to the wing, and every joint in that chain added a bit of friction and a bit of free play. A swept-wing jet at maritime patrol speeds gave the pilot no natural feedback through the column anyway, so the system added artificial loading for a set of springs to give the pilot something to push against. Cable and pulley slop on one end, spring resistance on the other, and the result was an aircraft that didn't feel right at the lateral axis and was by some accounts not always pleasant to fly. The spring loading had never been entirely satisfactory on the airline either. Blackman and Harrison went to Cunningham about it. Cunningham, who had flown the original Comet 4 and carried the political weight that had put him in the left-hand seat of X-Ray Victor 148, said, "Yes, I don't know why they made them like that. From what I've read, Blackman and Harrison looked at one another and said nothing. Firms get paid for delivering aircraft that meet the safety requirements, not for delivering ones that test pilots would have preferred to fly. The aileron system was inside the safety requirements and the contract was a fixed price. The schedule had no room in it for redesigning a system that worked. The Nimrod flew with the aileron system as carried over, with the adjustments to the artificial load-in and with friction reduced where it could be. The second prototype, X-Ray Victor 147, made its first flight on the 31st of July 1967 with Tony Blackman in the right-hand seat. He'd been on the Avro bid team since 1964 and had pushed for the engine shutdown case to the design office. 2 decades later, he wrote the memoir from which most of what is known about the test program's internal politics comes. This second prototype was the avionics testbed, with the new nose, the pannier, and the magnetic anomaly detector boom. The avionics fit needed 4 times the electrical power a Comet 4C carried. On X-Ray Victor 147, the Avon engine testbed, the clumsy interim answer was 4 60 kVA alternators in external air-cooled pods slung under the engine bays, shaft driven off the Avons through bevel gears. The production aircraft did it properly, 4 oil-cooled alternators mounted on the Spey engines. After Blackman's first flight from Woodford, it went to the Royal Aircraft Establishment at Farnborough for navigation trials and stayed in research work for the rest of its life. By this point, Harrison was running the test program. The crossfeed air duct in particular was his to demonstrate. 3 months after the first flight, with X-Ray Victor 148 past 60 hours in the air, Harrison told a public meeting that early trials on engine shutdown and restart procedures had shown asymmetric flying, including landing, to be completely innocuous. The asymmetric flying trials were repeated under a range of weights and configurations through the rest of 1967 and into 68, with engines shut down and restarted at various points in the search profile, and the system worked as it was hoped. The first of the 4 initial production Nimrods, X-Ray Victor 226, flew at Woodford on the 28th of June 1968 and was the first aircraft built from new to the Nimrod standard rather than converted from a Comet 4C. It was also the first production aircraft to carry the full magnetic anomaly detector boom. X-Ray Victor 147 had flown with an experimental fit. From X-Ray Victor 226 onwards, every Nimrod had it as standard. The boom had to be cleared aerodynamically. The added keel area aft would push the directional stability one way or the other, and the dorsal fin had only just been enlarged to push it forward. The first 4 production aircraft were spread across the test program. X-Ray Victor 226 took engineering systems such as air conditioning, autopilot, tropical and cold weather environmental work. X-Ray Victor 227 took armament, including clearance for long-range fuel tanks in the weapons bay. It was also fitted with permanent fatigue monitoring equipment and stayed a test aircraft for the rest of its service life. X-Ray Victor 228 went to Boscombe Down for navigation and tactical system assessment and afterwards flew weapons trials at Ortec, the Atlantic Underwater Test and Evaluation Center in the Bahamas. X-Ray Victor 229 took communications. X-Ray Victor 148 went to the Aeroplane and Armament Experimental Establishment at Boscombe Down between May and September 1968. While it was there at Boscombe Down, HMS Resolution slipped her moorings at Fastlane and went to sea on her first deterrent patrol. The boat the Nimrod was built to protect was now operational, but Nimrod was not. X-Ray Victor came back to Woodford for further development and was prepared for missile trials from February 1968 and then went out again for tropical trials between July and October that year. The flight test program that had begun on the 23rd of May 1967 was substantively complete in just over 2 years. The contract had been signed in January 1966, meaning that in just 3 years and 9 months it went from a fixed price contract to a service cleared aircraft. The delivery was on time and on budget, a remarkable achievement almost taken for granted at the time, and one nobody would expect to see again from British defence procurement. TSR-2 had been cancelled in '65 and the F-111K substitute had itself been cancelled in January 1968, Against that record, an aircraft delivered on the dates the contract had set was the exception that ought to have set the rule. However, meeting the deadline was paid for by accepting Shackleton era avionics. The carried across control system, the inherited pressure hull, the design choices made to fit the contract's time and money rather than to fit the aircraft's role. The real bill would only be known when the aircraft had to be refitted and show what the speed of the program had cost. What had been built was a jet airliner turned into a hunter of nuclear submarines, the dash speed of a 1950s passenger aircraft and the loiter economy of a propeller patroller. A magnetic anomaly detector that could resolve a signal a fraction the size of the Earth's own magnetic field, slung in a boom behind what was in spirit a Comet fuselage. A computer with 8 kilobytes of memory coupled to an autopilot flown by a navigator at the back of the aeroplane. Engines that could be shut down at search weight and restarted at transit. The Nimrod could leave its base in Kinloss, fly 1,000 miles into the North Atlantic, hold a search box for several hours, identify a Soviet submarine by the noise it made, drop a torpedo on the mad mark and fly home. The first production Nimrod MR1 X-Ray Victor 230 was delivered to number 236 Operational Conversion Unit at RAF St Morgan, Cornwall on the 2nd of October 1969. For 8 weeks the aircraft belonged to Coastal Command, but on the 27th of November 1969 Coastal Command was disbanded. The disbandment was marked with a flypast of 9 Shackletons over St Morgan. The aircraft built to replace the Shackletons took its place at the back of the formation. The same day, number 18 Maritime Group of the Strike Command was formed. The aircraft was delivered on time, on budget, into the service it had been built for in the month it had ceased to exist. What that counted as depended on where you stood. What the aircraft did next is for part 2, which will be about what the Nimrod actually did in the secret war over the North Atlantic, the boats it hunted, and the men who called themselves the Magic Circle. So a big thank you to my old man. He hates it when I call him that. Bless him for clearing out my old bedroom and finding my old warplane magazines, and only the warplane magazines. I'm not a spring chicken, by the way, so this room has been, let's say, it's been mine in name only for some time. I really need to have a good old rummage around and see what else is in there that I've forgotten about. Nostalgia is a hell of a thing. So thanks again to Surfshark for sponsoring and inspiring this video series. A link down below for surfshark.com/Aviation Republic, and use the coupon code Aviation Republic at checkout for an extra 4 months of the service for free, because you don't want anyone rummaging around in your stuff. So see you in the next one. Toodaloo.